Yeah, so a couple of weeks ago I was started to contemplate this talk and what I was going to talk about. And I think at the time the title of this presentation was Powerful Native Code Builds in Gradle. And I was like, okay, yeah, I can do a bit of a showcase of what we've done in the last 12 months and demonstrate some of the features, and that'd be kind of interesting. And but I was trying to, there's a couple of worries there. One is that I've got this, we're doing a workshop tomorrow afternoon, which is 3 hours of hands-on, let's build some stuff. Use the native stuff to build some code. And so it's like, well, what are we how can I make this interesting? And also I thought maybe there's not that many people actually who are C++ developers here or native code developers. So I wanted to kind of draw some of Ben's attendees over to my talk, so we didn't end up with like 3 people in the back row, something like that. So I sort of thought, how can I make this more relevant? So I'm curious to know if that was worthwhile. So who here has done any sort of native development in the past at any time? Okay, yeah, quite a few. So keep your hands up if you are still doing native development in your day-to-day life. And then keep your hands up if you've tried out the native stuff in Gradle. Okay, a few people. And who's using that to build production code? So 3, there we go, something like that. So I kind of thought, yeah, if I'm going to be talking about how to include Windows resources in a DLL or how to integrate with CUnit, it might be interesting to 3 people, and the rest of you are going to be sitting here checking your emails, cursing the Wi-Fi as you do at conferences, So I thought, maybe I'll try to jazz it up a little bit. So put on my marketing hat, and there we go. Change the title. This changes everything. But the goal, so I sort of changed the tack of the talk a little bit. What I want to talk today is about how some of the things we did when we added native support are really interesting and really fundamental changes to Gradle. And these changes are part of this vision that Hans talked about a bit this morning about how Gradle is going to get better in the future. Some deep infrastructural changes we made, some really strategic decisions we've made. And when you look at the native support we added in the last 12 months, it's a bit of you can see some of the aspects of what we're going to be doing in say, Gradle 3.0. So some of the things that you're going to see in the future as a Java developer, as a web application developer, these things are going to start coming into your domain soon. In the next 6 months, the next 12 months, you're going to start seeing some of these concepts. So I want to talk today a bit about the native support and also about some of the high level, how we made things, how these things are going to affect you in the future. So, and as I said, tomorrow there's the hands-on workshop. If you're really interested in the nitty-gritty of how to get things built with Gradle, feel free to come along to the workshop. So, firstly, a little bit about me. So, I'm Daz. My name's actually Daz DeBoer, but everyone calls me Daz. Funny story, yesterday I met a guy and I said, oh, yeah, hi, I'm Daz. He goes, D-A-Z? I said, yeah. He goes, I was wondering what to-do Daz meant in the code. I was looking through the Gradle code and there's all these to-do Daz. And he thought, what's D-A-Z stand for? My bad, that's me. I haven't finished stuff, so yeah. So it's a common Australian nickname. So yeah, I currently live in a small town in the Canadian Rockies. I'm what's called a lifestyle refugee there. So I left the city and I moved to a little town. And before I joined Gradleware, this is what I looked like. I was snowboarding and mountain biking and had a good work-life balance. And then somewhere along those 1.5 million downloads that Hans was talking about, my work-life balance sort of correlates inversely with the number of downloads of Gradle. So I've started working more and playing less, but yeah, so that's who I was anyway. And at Gradle, I guess from the technical background, I've been working in build tools for a long time. I was involved in Ant early on. Adam, one of the founders, and I were involved in an Ant 2.0 project, probably about 12 years ago. We were going to revolutionize Ant and bring out, it's all going to change. And I guess Ant's now at 1.9.3. So the revolution was squashed. We moved on, and so Gradle was born, 5 years later or so. So that's a little bit about me. One thing that I'm not is I'm not a C++ developer. So I just want to be upfront about that. Hello World was a challenge for me at the start of this project, at the start of doing this work, and particularly assembler. It took me a while to get my head around it. I had a lot of help from Adam, who is a seasoned, hardened native developer, and I've got a lot of build tool experience. So together we sort of work things out. So if you have any really tough, specific native questions to ask me, I may not be able to answer. But if you have things around compiling and linking and stuff, I generally have picked it up over the last 18 months or so. All right, so I want to talk a little bit about how we got to the point we're at today. So there's been some basic C and C++ support in Gradle for a long time. So probably for 4 years. 4 years ago that we added some pretty simple little plugins to compile and link C and C++ executables and libraries. They were just built pretty much the same way the Java plugin and the Groovy plugins are built. They weren't very widely used, so we basically, we sort of didn't get any. There's no support requests on the forum about them. There's no customers coming and asking us to improve them. So you sort of get a feeling these are just toy projects. And we said, okay, cool. We didn't invest a lot in them. We didn't have a lot of time to invest. We focused on other things, and sort of they were left idle for a little while, until early last year. We got approached by a customer, and this customer said, hey, we'd really like to work with you to make Gradle a great native code development platform, native code build platform. And we're like, wow, yeah, we'd like that. That sounds great, so why are you coming to, why Gradle? Why are you choosing Gradle? And they said, well, these are a sophisticated shop. They've got hundreds of developers, C, C++, assembler, building for embedded devices, building for lots and lots of platforms. And they just said, okay, well, what we did is we got together and we did a really thorough analysis of the tooling that's available. They looked at their current system, which was built on Make and Perl scripts, and they go, well, yeah, we could hack something together ourselves for that, but that's not our core. It's not our core competency. We don't want to build our own build system. We'd like something that works for us. And they looked at scones, and they did a pretty good analysis of scones, and it was promising. It had some interesting dependency management features in there, but what they wanted was a really rich tool that didn't just compile and link, but actually supported the full automation of software delivery, sort of what Gradle's really good at. And so and for some reason, one of the guys had found Gradle and thought, hey, let's put Gradle into the mix and let's investigate. And the decision they came to is that of all the tools they could find, the best candidate to be a great native build platform was Gradle. And the only problem with Gradle is that it's not a native build platform. So, they had everything else, like it had the extensibility and the flexibility and the support and the active community behind it, that they sort of thought that's something we can jump on and make better. So working together with those guys, we spent probably 9 months last year doing pretty heavily investing into our native support. And where we've got to now is a pretty solid platform for building native code. It's rough around the edges in places, and it doesn't, it hasn't been battle hardened, I guess you'd say. But it's capable, and it's got some pretty cool features in there. So we started with, there was a bit of a feature list that came, that's part of the input into this development process was this feature list. So we sort of said, okay, and we've addressed most of these things in the last 12 months. So building executable, static and shared libraries, building with C, C++, assembler, Windows resources, IDL, Objective-C, Objective-C++, a bunch of different languages. Using different tool chains, so Visual C++, GCC, Clang as well is supported now. Building multiple variants. So one of the things that is obviously vital in the native space is be able to build for different platforms, or build for different build types. So that was that was a pretty important feature we had to throw in. Incremental compilation, because compilation in C and particularly C++ is slow, and we're kind of, in the Java world, we're kind of spoilt. We can sort of just compile, not worry about it too much. But in the C++ world, it can be a huge overhead if you have to compile multiple times. So just incremental compilation was really important. Into project dependencies. So part of the high-level feature list is full dependency management. You look at what we have, the tooling we have in the Java space, and you go, well, that's what we want in the native space. We want it to work like that. We sort of scaled back the requirements just for the last 12 months to say, let's do this within the project. So just at least if you have a multi-project build, you can build a library and have real dependency resolution between the things you build yourself. We haven't yet got to the point of the publishing and resolution, which is what we want to do next in the native space. Integration with CUnit, which is effectively just give me what you get for JUnit and TestNG I want the same sort of functionality for in the native space. And Visual Studio project generation. So again, what you guys can do in Java, that's what we want to be able to do in the native space. So this is kind of the feature list of C++ native features that we wanted to that got thrown into the mix, and okay, that's what we're tackling. But there were a lot of other things that that fed into what we decided to do. Now, some of these were sort of, I guess, opportunistic. We sort of have been thinking about things for a while. Like, it'd be really great if we could add some of these features. And some of these were absolutely essential. We couldn't implement the native support without them. So, an example of, yep, sure. An example of, I might just wait 1 second. Okay. Of something that was sort of opportunistic, we've been thinking about it for a while, was adding a much more expressive software component model. So we've seen this already in the Android plugin. There's a really expressive DSL that isn't so task-focused. It's really focused on what you're trying to build, and we went, wow, we want to do something. That's the sort of thing we want to do. And we've also, this has been bubbling along in these sort of new Ivy Publish and Maven Publish plugins that were added like 18 months ago and sort of haven't really progressed too much. But the idea that there's components that you're publishing is sort of a pretty powerful concept that we've been trying to pull in, and part of the native work was, okay, let's do this properly. Let's get a real software component model that we can use. We had rule-based configuration was something we've been thinking about for a while, and Hans mentioned it this morning in his keynote. Adam will be talking a bit about it tomorrow. But basically, native code, although it doesn't require that, it expands. I'll talk about this in a little bit, but it expands the need for those things even more. Binary variants I've already discussed a bit. The need to be able to handle multiple outputs for the same set of sources. It's kind of, when you think about it, it's kind of ridiculous we haven't dealt with it in the past. We haven't dealt with it well in the past. And thanks again to the Android guys who sort of, they needed this, so they pushed in it. They forced us to make some changes in the Java world, and we sort of then adapted some of those into the native world. And I'll talk about that quite a bit and all the dimensions of that during today's talk. And finally, domain-aware dependency management. So Hans this morning mentioned variant-aware dependency management, but it's more than that. It's variance is a part of this domain model that we're trying to capture, and other things like, rather than just treating dependencies as some abstract thing that turns into a set of files, we want to think about it in terms of this component model. So our dependencies are on components, and when we resolve, we'd like to be able to get those in terms of components and and the artifacts for a component are really just, they're like little leaves of the model. They're not the core part of the models. So these are the, so what I'm going to talk about today is, I'll be talking a little bit about the native language features. I'll be spending quite a bit of time talking about the component model that we've developed, and that's going to feed into all of the domains in Gradle. I'll talk a little bit about the rule-based configuration, because Adam's going to talk about that quite a bit tomorrow. Talk quite a bit about the binary variants and the model that goes behind that. And at the end, I'll talk a bit about dependency management and the domain-aware dependency management. So after each section, I'll probably stop and see if I can ask questions. I'll stop right now. Has anyone got any questions that they want to ask before I dive in? Yep.
Have you looked at Eclipse CDT project generation? Does that work?
So in the very early stages, the early plugins that I mentioned that have been around for years, there was Eclipse CDT project generation, and the answer is no, I haven't looked at it. So the test coverage still passes, but it's sort of not something we don't officially support it. There's no documentation on it, so that sort of thing. So yeah.
And then, one thing we've heard when we talk to people about this at this stage is the kind of the startup cost, right? You're running a JVM file.
Yeah.
So one thing people mentioned was something called Ninja. So you can take CMake, create Ninja, which is a very low-level build system that runs really fast for development iteration. I was wondering if you had any thoughts, if you'd heard about it.
I haven't heard about it. I mean, I can understand.
Can you repeat the question?
Oh yeah, sorry, good idea. Yeah, so the question was about Ninja, which is, I don't know anything about it, but I can imagine what it might be, which is basically like a serialized form of your, like a local, fast, probably denormalized form of your build script. Yeah, ready to.
It runs super fast.
Yeah. I guess part of you could think of the new configuration model with 0 configuration time as being something like that. So I will talk at the end a bit about performance and what we need to do more. Not being a C++ developer probably makes me less performance centric as as people who've been working in that world for a long time, where everyone, that's all they think about, it seems. So, but yeah, I can talk about that a little bit more at the end. Okay, so we'll talk a bit about the software component model. So Gradle's always differentiated itself from other build tools on having a domain model. So having a pretty rich programmatic model of what you're trying to do. So we have plugins, and you can programmatically access plugins and tasks. Tasks and inputs and outputs have been modeled in quite a rich way, so you can access those programmatically. Source sets are quite well modeled in Gradle. So there's quite a rich domain model. But one thing that we've kind of probably one of the downsides, or one of the things we haven't quite modeled well, is we've modeled a build system. We've modeled how builds work, and we haven't always modeled the software that you're trying to build. We haven't always modeled what I as a developer am working on. We've modeled our domain, which is the build domain. We haven't modeled the software domain so much. So at times the software domain that we're building has been quite implicit. So you apply some plugins and you end up with a domain, like you end up with this implicit domain there, but it's all represented in tasks and plugins and things like that. So again, yeah, Android sort of led the way with a richer DSL that sort of said, we don't want to say, here's the tasks and configure those. We want to configure a domain model of what we're trying to build. And so let's just go back and have a look at what we do currently in the Java world. So we apply a Java plugin. So effectively what we're doing there, we're saying, okay, I've got Java language sources, and I'm trying to build a library that runs on the JVM. So there's kind of this implicit model. We're building a library that runs on the JVM. We apply the Groovy plugin, and that says, it actually applies the Java plugin and says, okay, so we're still building a library that runs on the JVM, but now we've got Groovy sources as well as Java sources. And then we apply the War plugin. So what does this do? This says, actually, I no longer want to have I'm no longer going to produce a Java library. I'm now going to produce a web application. So there's actually this little, disable the task that produces the jar. You can re-enable it if you want to. So sort of, suddenly we've got this, I think it's pretty clear that this is not a very expressive way to tell Gradle what you're trying to build. Applying plugins is not a rich way to express this stuff. So it's worked for now, but we sort of, and we tried to do this in the native space. So we said, okay, we started with a CPP exe and a CPP lib plugin. So you can probably imagine what those do. But then you think, okay, well now we need C, assembler, Windows resources, Objective-C, Objective-C++. We've got to add all those supports. So do we add just language plugins for those? Do we add combinations of those for kernel drivers and all the other types of things we might want to build? It just doesn't really work well. So we thought, actually, let's make it explicit. Let's say, what do I want to build? So this is how you define what you're trying to build in the native space. So applying the C++ plugin, that's basically adding some capabilities to build. It's not saying what you're trying to build, it's saying what capabilities are available in this build script. You then have an executables container. So this is part of the capabilities. Part of the plugin adds the container, but what I'm doing here is I'm specifying that I'm building a hello world executable. So this is explicit. We're saying that's what we're trying to build. We're also trying to build a greeting library, native library in this case. So it's maybe not immediately obvious, but one thing that this has done is it actually separated this implicit tie between the Gradle project and the output you're trying to build. So in the past, it's not been that simple to say, I actually want to build 2 jars from this Gradle project. Like, it hasn't been impossible, but it wasn't really obvious how you would do that. And now suddenly we've got 2 components, same build file. It doesn't matter, like the build file structure is not necessarily tied to the component structure you're trying to build. So it just adds a lot of flexibility there. You don't have to have multi-project builds if you don't want to. If you want to just have 3 things you're building in one project, you don't have to have you know, a root project build with 3 sub-projects. So yeah, so what we're trying, and so I think it's pretty clear here, we're defining what we're trying to build. So some of this stuff is already being moved into the Java space. So we've actually got, this is in, I won't say it's in Gradle 2, but it's definitely in master now. We've got a couple of new plugins. The JVM component plugin, which adds the concept of JVM libraries, and we'll later add the concept of, say, a JVM executable. It may add other types of JVM-based components. And we have a Java lang plugin, and that adds the Java language capabilities, but doesn't add the components that you're trying to build. So you can imagine we can have Groovy lang and Scala lang, and maybe one day, we haven't quite worked it out, but maybe one day we'll use GCJ and actually compile Java lang to a native binary. You know, the Java language is not inherently tied necessarily to a JVM. So we want to kind of detangle these things a little bit. And yeah, this stuff's already in master. It's a little bit different because we now have a namespace for the actual domain you're working in, and we'll have the similar namespace for native stuff. So we'll say have native code and then executables in there. So yeah, just to show you that we've already started moving this stuff into the JVM space. The future for this is sort of like we started thinking about, okay, well, like a kernel driver. We want to be able to build a kernel driver. We don't want to say, I'm building an executable that has these properties. We want to actually model that. We want to say, how is it different from a library or an executable? Because it is, you know. A JEE web application, that's a thing that we want to be able to model and say it has these, it depends on these APIs and it has these attributes, and we can sort of start to model it better. A Gradle plugin would be another one we want to do. So you can imagine here, Gradle plugins, my Gradle plugin, and suddenly all of that capability around how, you know, all the sort of deep domain knowledge about what a Gradle plugin is can be there. So it's sort of a pretty powerful concept, and it's just suddenly going, oh, let's make it explicit, and then we can build, like you don't have to define everything. There's still conventions that we define around. For a library, we're going to define some source sets because, you know, by convention, we're going to define some binaries by convention. It's not like you have to define everything explicitly, but actually just having the component model up front has made a big difference to how we think about things. And yeah, so one of the things the major things that's changed in the way we think about things, and we're sort of moving things more and more, is this concept that telling us what you're trying to build is better than telling us how you're trying to build it. So if you think about what we do in Gradle 1 or Gradle 2, you spend a lot of time configuring plugins and tasks. You spend the time thinking, okay, I want to take these sources, I want to compile them and put the outputs there, then I want to zip them up and put the output there. So you're basically saying, Gradle do that, and Gradle do that. And then Gradle goes, okay, cool, I can do that. But if you instead say, what I want is those sources compiled and zipped here, by saying what I want is the compiled and zipped output of those sources, suddenly Gradle has a bit more flexibility to say, oh, actually, yeah, I've got one of those from earlier, or I've got, you know, we're not focused on how the mechanics of how things are trying to happen. We're focused on the output that we're trying to get. And so it's actually a really powerful way to look at software, to start modeling in terms of what you're trying to build rather than how it's trying to be built. So something that a few people, if you come from the Java space and start using the native space, you start thinking, well, sure, but I've lost everything I've ever learned about Gradle. It doesn't help me anymore. You know, suddenly I'm no longer a Gradle developer. You know, where are the tasks? And I just want to reassure you, the task execution graph is still there. So anytime you execute a build with a C++ plugin, there's a task execution graph built, and we still have the dependency graph there. The tasks are all configured individually. There's no change there. In fact, all of the native stuff was built on top of the existing infrastructure. There's no new deep infrastructure built at that level. So, but what we do is we build a domain model, and then we construct tasks for that domain model. So we configure the domain model, and then we can configure the tasks. The nice thing about that is if you say, I want to compile and link, and I've got to use these arguments for compiling this and these arguments for linking this, those arguments can be together on the thing you're trying to build rather than be separate on the tasks that you're trying to use to build them. So you're not saying, when I compile for Windows, I use this flag, and when I link for Windows, I use this flag. You can say, when I'm building for Windows, the C compiler uses these arguments and the linker uses these arguments. You can sort of keep that knowledge encapsulated together. Another interesting thing is, so our domain model, a lot of the elements within the domain model are buildable. So you think of a domain model element, you're saying, okay, how does that map to the task graph? A buildable model element is effectively, has a life cycle task that gives you an entry point to build that thing, and also can depend on other buildable model elements or on other tasks. So effectively, you can say, the really nice thing is those source sets in the native space are buildable model elements. So if you want generated sources, you just say, this source set, here's a task that it depends on. Whenever you have anything that uses those sources, that task is going to be run before they get there. So it's something that's really easy. And when you start, when you have these buildable model elements, it's really easy to insert your own bits of logic within the task graph that's generated from the domain model. So yeah, the key. So yeah, the key concepts behind the key domain elements we've got so far are the sort of source sets, libraries, executables, and we have test suites as well. We're building these in the domain model, but there's going to be a lot more that's going to come. So I'll quickly talk about the language support in the native space. So straight up front, we went, okay, this can't be an ad hoc solution to multiple languages. We can't go, oh no, we have to add another language. It's going to be really hard work. It needs to be straightforward to support, because straight away we had, I think, 7 different languages, or 5, and then we added Objective-C and Objective-C++, and you've got 7 languages to support. It becomes important to make this a lightweight process. So we did a little bit more modeling around source sets and so the source sets in Java. We did a bit of modeling to take what we have in Java, which are pretty simple concepts of source sets, to make it a bit of a bigger concept. And we what we have is so for every time you add a component to the model, we're adding what we call a functional source set to the set of sources available. So the component's called hello. There's a functional source set called hello as well, and then we have a language source set for each of the languages that are supported. There's automatically a language source set added. So in this case, we've got an executable named hello. It means we've got a functional source set named hello, and there'll be a hello.cpp C++ source set and a hello.c C source set. And this is just an example of how you can configure the actual locations of the directories where those sources are held. So one interesting thing is that this points out is that so in the Java space, sources are just one type, but in the native space we have the C++ sources actually consist of a bunch of header files and a bunch of source files, and they're used in different ways at different times. So the source sets need to be a little bit more flexible, and they have a few more attributes than they do in Java. So here's an example of how we can add an additional language source set. So here's our functional source set named main, and what we're doing here is we're saying there's already going to be a main.cpp language source set, but we're actually adding another one, which is a Windows C++, Windows CPP. It's another set of C++ sources. So that line there is effectively just adding another language source set. What this slide also points out, which is interesting, is a source set can have a dependency on another source set. So this source set is actually dependent on the main C++ source set. And what that effectively means is the headers in the main C++ source set, or the API of the main C++ source set, is available when compiling the Windows C++ source set. So it allows you to compose source sets up, and we think it's a pretty powerful concept. So there's actually, this concept is actually underpinning the core Java plugin already. So these language source sets are already there. They're already being used in all the Java language support, but it just hasn't sort of bubbled up to publicly consumable things. So you'll see in the next 6 months that more and more of this stuff will filter into the Java world, probably into the JavaScript space as well. So I've got a demo I might switch to a demo, but does anyone have any questions before I move on to a demo there?
libraries and have one link against the other or something like that?
So yeah, so the question's about, yeah, if you have two types of sources, shared headers, yes, you basically define a C and a C++ source set, and then those will be compiled separately and then linked together. So they can be part of the same component. So the example here.
Right under the CPP.
Well, so I guess you don't have to have this configuration. So there's conventions that define where the actual where their files are found. So yes, there is actually a C language source set as well. It's just that I didn't have room on my slide to show the configuration of that as well. So yeah, in the same way that here we've got this actually exists. This main CPP source set exists, and we're only explicitly configuring the one we're adding. Yep.
How does the name of the source set affect when you call Windows CPP? How do you express that this is only for Windows?
So the question is, what is the name of how's the name of that language source set affect the build? You need to explicitly add it to, so you can explicitly add it to a particular binary. So you can say, okay, this binary I want to build with that Windows source set. Or you can compile with different arguments. So you might say, I want to compile this source set with different arguments. So it's a name that you use. It's not a name that the name is not significant to Gradle. The names of the functional source sets are by convention the same as the names of the components you're trying to build. But that's just the convention we built in, and the names of the built-in language source sets are by convention the names of the languages, but that's all just conventional. So if you add your own, so yeah, I didn't show there how you would wire in your own language source set. I just showed how you would actually create it. So I'm going to do a quick demo if I can manage to get Keynote to behave. Awesome. Okay, so we've got so what I'm going to do is just do a really simple Hello World application with Gradle, just to sort of demonstrate a few of the things we've done so far. So what I've got is, I'll do a clean so we have what we need. So we've, and I'm going to remove the build.gradle file that I created earlier. So what we've got is really simple layout here. We're using effectively we had to choose a default layout for C and C++ projects, so we thought we'll keep it the same as the Java one. I don't think there is a convention that exists in the world of C and C++ developers, so there's no point trying to find one and trying to codify it. So I'm using the convention. I think in most cases you'll need to configure your own. So what we've got is a main CPP file, which just is the entry point to the executable. Includes the hello.h file and calls the hello method. And then we have a hello service here, which is actually going to be, which actually has the implementation of that method and the header. I don't think you need to see them because there's nothing interesting in the actual code. What's interesting is going to be in the build. So let's start off with a simple Gradle file. And I'm going to apply the CPP plugin. So first thing we want to do is look at, so if we were in the Java world, that would be all we need to do. That's like, we would then have a fully functional build. In the native space, we don't. So if you look at what tasks we have available to us, we've got our standard assemble and clean, all the built-in tasks, but there's nothing in there to build a C++ application. This is because we've decided, let's make it explicit. So let's have a look. So first thing we want to do is I'll add the library that we're going to build. So I think it's hello service. And let's have a look at what tasks we have available now. So now you can see we've got a couple of tasks. We've got a shared library lifecycle task and a static library lifecycle task. So this is effectively the name of the binary the binary in the model. And it's the lifecycle task that relates to that buildable model element. So we've got two different libraries defined, two different library variants defined, and we can try executing one of those. So I'm going to try do this. I'll build the shared one. So what's it called? Hello service shared lib. So let's have a look at what's happened here. There's a compile task for the hello service.cpp language source set. So we've got a compile. Here's the name of the actual binary we're building. That's the name of the language source set we're building. It's kind of a long name, but luckily you didn't have to ever write that down, and you don't have to type it in ever. Here we're linking the actual shared library, so we're linking all the outputs of all the compile tasks. In this case, it's only one. And there's that lifecycle task, which is actually the entry point into the model or into the task execution graph from the model, or the link between the model and the task execution graph. Yep.
What compiler and what version did you run on the backend, or did Gradle run on the backend?
That would be running Clang. So I'll talk about toolchains a bit later on. So
And have we thought about GCC?
Oh yeah, it's fully supported.
Okay.
Just not on the Mac because, no, it is supported on the Mac, but by default, Clang is in the path. Oh, sorry, I've got to learn how to repeat the questions for the. So the question was, do we support GCC? And the answer is yes, but Clang is being used right now in this example. So let's get the executable built. So I'm going to add an executable to the executables container. And let's try building that. Let's have a look at what tasks we have first, actually. So we've got a hello executable lifecycle task, and we have an install hello executable, which basically gets the built binary and bundles it up with any libraries it needs so that it's executable in a sort of development environment. So I'll try running the executable task. That should do. And we got a failure. So does anyone know, can anyone think why we have a failure here? Anyone? That's exactly right. So you could say we don't have access to the header file, but actually the modeling way to think of it is we didn't hook the library to the executable. So there's a few different ways we can do this, and I don't want to, because I'm going to talk about dependency management a little bit later on. I won't describe the syntax in too much detail, but basically we're taking our sources.hello.cpp, so that language source set, and we're saying it depends on a library called hello service. And if I got that right, we basically, so what we've done now is we've compiled all the hello executable, the hello CPP, hello.cpp source set for the hello executable. And then these things were all up to date because we'd already linked and we'd already compiled and linked the shared library. We're then linking the hello executable, which is both, it's linking in the compiled output, the compiled sources, as well as the .so file from the shared library. We're building a hello executable, and then we're installing it. So let's have a look at what we've got in our build directory now. There's a few things there. So we've got two binaries built. So we've got a hello executable binary, or a hello in the hello executable binary, and a dilib, which is actually what a .so file is called on a Mac. So it's effectively a shared library called lib hello service. That's in our binaries. They're the sort of the isolated binaries. You can't, if I try to run this version here, it just won't have access to the shared library it needs. So then we've got this little install image of the hello executable, and it's got the actual binary taken from here, as well as the shared library here. Actually, that's a shell script that wires the things together, and that's the actual binary. So I'll just quickly, might as well try running it, I guess. Hooray! All that work. So let's just have a look at the Gradle build.gradle file. So just so we can run over it again, all we've had to do is define that we have a hello service library, and that we have a hello executable, and we wired the two things together by saying the C++ sources for my hello executable depend on a library called hello service. So and I'll talk a bit more about what that means when I talk about dependency management a bit more. So, perfect. So, any more questions after the demo or anything like that? Yep.
So, admitting that this may be something that we native people have to let go of, is there a way of seeing the actual commands that are being run other than Gradle-D, which gives you so much output that it's hard to actually find the commands?
Yes, so there is a way to see, because what we do is we use a options file for running the compiler whenever the compilers support it. That's an easy way to see what Gradle ran. So I shouldn't have switched back. So if we look at, I'll just open one. So in the build directory, there's a temp directory. I mean, this is kind of implementation details, but at least it's useful for now. So if you want to see how the hello CBP sources were executed, we can have a look at that. And they're all the commands that are provided to the compiler when it was built. So I think that there certainly would be useful to add, say, something we can do at -info or something we can explicitly add to say a dry run where you can see what's going to be run rather than actually running it. So it does show an info. Oh, there you go. Cool. The full because it's using the XE task or the exec task that does the command line at info. Okay. So yeah, but this is a way of seeing. This is kind of the source of truth. This is what Gradle's actually passing to the compiler at the time. So. There was another question, I think.
Variants. How do you build for different architecture?
We'll get to that in a little bit, yeah. Anything else? Okay, cool. So back to this one. And excellent. Cool. So that was the sort of the software configuration model, the component model that's sort of been added in the native space, and what you'll start seeing more and more in the other domains as well. Something Hans talked about this morning quite a bit, and Adam will probably be talking about a lot tomorrow, is this new configuration model. You know, Hans put the big 0 up there. It was kind of exciting. You know, no configuration time. I just want to talk a little bit about why in the native space this is vitally important. So there's two reasons we need some sort of rule-based configuration as opposed to programmatic configuration that we have now. The first one is performance. So if you imagine in the Java space, configuration time can be a bit of a pain sometimes. You know, let's say you have 100 sub-projects and you've got to configure all the jar tasks and all the compile tasks for all those 100 sub-projects. There's a fair bit of work for Gradle to do there. But let's step into the native space for a while. Let's say you have 50 sub-projects in a multi-project build, not a huge build. And then you have a couple of components per project, so that's 100. Then you have, say, 3 build types per component, so that's 300. Now you've got 5 platforms you're supporting, so there's 1,500, and then you've got 2 flavors for each of those. That's 3,000. That's 3,000 components we're trying to build. Now let's think, okay, now we've got maybe 10 tasks per component that we're trying to build. So we're just talking about 30,000 tasks configured, just to work out what might be executed. And you can see straight away that this variant explosion is going to kill us at configuration time. So I'm not saying we've solved that as part of the native work we've done so far, but it's like a magnifying glass on it. You start building, if we want to be able to support the same size of projects in the native world as we do in the Java world, we need to solve this problem. We already need to solve it for Java, but we need to solve it even more desperately in the native space. So that's kind of the performance side. You know, why we need to tackle the configuration. And the other issue is simplicity. So it's sort of handling more complex domain models or more complex plugin interactions, what have you. And I think Hans touched on that today. But an example we have, which is really it's a pretty simple example, is say. We said, okay, well, we want you to be able to define the available tool chains. We want you to be able to say, I only want to use that, and these 2 tool chains is all I want to use. But then we also want to be able to say, if you don't tell us any tool chains, we want to add the defaults. We want to say, okay, here's the 3 default tool chains, and they're always available if you don't tell us anything. And so you start going, okay, well, maybe we'll start with the container with some things in it, and then we'll remove them when you first add it. But then we have these lazy containers, which as soon as you add anything, it trickles through to the rest of the configuration model. So when we add the defaults, they automatically set up a whole bunch of infrastructure that we don't want. So then we thought, okay, let's do it after we've let the user configure the tool chains. Let's decide at that point that we want to actually, whether they need the defaults or not. But when is after? There's no, the only time you know that the user's finished is in that project.afterEvaluate. But how do you know that the user hasn't got a project.afterEvaluate and that theirs isn't going to evaluate after yours? So this ordering problem, even in a really simple case like I want some defaults, is killing us, right? It's kind of, so we basically implemented like, okay, we added a little hook. There's a little hook in between before project after evaluate and after all the configuration. That's so we go, oh, we'll just use that, but it's not a solution, right? This is like, okay, we can't infinitely add hooks there. So basically, the configuration model, the new configuration model is going to help. We haven't done this yet. Like, we haven't solved these problems yet, but we've identified these problems and they're very clear to us. And some of the new configuration model is already in evidence in the native space. So you'll see this model element quite a lot. So, and this is basically everything inside the model block are model rules. So they're configuration rules. So don't worry too much about how it works or anything like that. But just this is evidence of the new. You'll start seeing this more and more in your builds. You're going to start seeing either the model block or something that operates in effectively the same way. Also, we were really careful not to force you to iterate over things and not to force you to access things by name. So we don't want you to assume that that particular domain object exists, because that means we have to instantiate it. So we don't want you to iterate over all of them. What we want you to do is say, for every binary that is of this type, do something. And that's a rule. Then we can say, okay, cool. Then if we need to create one of those, we know the rules to apply. So you'll see this pattern used a lot throughout the native stuff, and that's the sort of pattern we'll get more and more. They'll kind of move into the rest of the domains as well. So yeah, I won't cover that anymore. Does anyone have any questions about the rule stuff? Because it's going to be covered a bit more in the talks tomorrow. Everyone understands it. Cool. Okay. Excellent. So we're getting to variants now. So this is a pretty big part of the work we've been doing in the native space. So what is a variant? Really simply, to me, in my mind, it's using the same source code to build multiple outputs. And if you think about it that way, you think, oh, that makes sense. We should be able to do that. And for a long time, Gradle hasn't made it really easy to do this, right? If you want to build 2 different jars from the same source files, it's not trivial to do. It's not impossible, but it's just not. It should be trivial. It should be simple. And Android had this problem. We ended up building some infrastructure underneath that allowed them to do this in a more easy way. And we leveraged that infrastructure for doing the native stuff. But it's not just in the native space we need these things. What about building like Scala is an example Hans mentioned. We have Scala. Scala's not binary compatible, so you have to compile for the particular Scala version you're using. What if you want to build an obfuscated jar and a regular jar that you want to use, and you want to have the regular jar there, but you don't want to, like they're both built from source, or what if you want to, like we never do this in the JVM world, but what if you wanted to build a debug and a production binary and didn't want to include the debug symbols in your production binary? I mean, there is a flag on the compiler, but because it's not that easy to do, no one does this. They just go, okay, we'll just include debug all the time, So basically, this sort of concept has been hard, and so we've sort of gone, oh, we'll just pretend there's only ever one output for a set of sources, and it's just not true. So the single output from a set of sources is pretty deeply ingrained in our dependency management model too. So we've sort of inherited this from Ivy and Maven, this concept that you resolve a module to a version, and suddenly you know what artifact you need, and that sort of it's so deeply embedded in our dependency management model that we need to start to step back and go, this is a bigger thing. Like it's going to affect every level, both when you define your build, to when you resolve, to when you publish, and to when you resolve. So we sort of stepped back and we sort of thought about, okay, what do variants mean? And we've sort of defined three major categories or dimensions that are that variants vary on, I guess. This is not set in stone, but this is kind of just the first cut at how we can model this stuff without it getting ridiculously complicated. So so variants currently have a flavor, have a build type, and have a platform. And I'm going to run through those things now. So the first variant dimension we addressed was flavor. So this is one that the Android folks use to differentiate different binaries, and we use flavor as basically it has no meaning to Gradle. It's basically, okay, you decide what the flavors of your application mean. Gradle doesn't go, it doesn't have any predefined sets of flavors. It doesn't sort of know if you're building this particular flavor, do this. It just says, okay, cool. There's something for you to use in terms of building variants. So if you want to define flavors in your model, so this is the way of saying my component has two flavors. It has a free flavor and a paid flavor. So by just defining that, you now have the ability to build two variants for every set of sort. For every component that you've defined, you get two variants, a free variant and a paid variant. They'll be exactly the same unless you configure them to be different. So this is an example of this is an example of a rule that says, okay, if the flavor's the free flavor, then add a macro, define a macro for the C++ compiler. So let's say you've got a really simple thing. We've got add enabled on our free app, so we're going to define the enable adds macro on our C++ compiler. So that's the first dimension we're looking at is flavor. It's pretty simple. Doesn't have much built-in context, but it gives you something to do, something where you can add your own sort of logic there. I guess eventually what we'd like to do is instead of adding flavor, have you add your own dimension and give it its own name and things like that. But we haven't got to that point yet. So flavor is kind of a bucket where you can throw the bits of logic that don't fit in any other dimensions. So we have build type. It's the second dimension we're sort of looking at. So build type is effectively, we think of it as kind of, if variants vary on a build type, they vary in a non-functional way. So they're functionally equivalent binaries that vary on some other aspect. So an example would be a debug, something with debug flags included, debug symbols included, or something without debug symbols. So there's a debug and a release variant. Somehow instrumented jar versus a non-instrumented jar would be another example of a build type. Something that's optimized and not, something that's obfuscated or not. These are all build types because effectively they're drop-in replacements for each other. They're identical for all functional purposes, but there's other sort of non-functional differences between them. So and I guess I mentioned, in the native space, it's really, we need these. It's a common practice to have a debug variant and a release variant. So you have debug symbols in your debug variant, and they're stripped out of your release code. So in the Java space, we don't do this very often, but it's probably something we're going to start seeing build types more and more when the capabilities are there to do it more easily. So the syntax for defining build types is virtually identical to the flavor syntax. We've got a model rule to add some build types. So we're just basically here, we're defining a debug and a release build type. So what I would like to be able to say is that's all you have to do. So in the future, that's how it's going to be. The tool chains are going to know, okay, I know how to build a debug variant, or we're going to have plugins that know to build particular type. We can apply the dwarf debug symbol plugin, and then suddenly debug variants are going to be built with those particular flags built. At the moment, it's up to you to do this stuff. So basically, you're gonna define the rules to say what these things mean. But these we believe and we hope that these will become sort of, we need to come up with some sort of strong meaning behind these things so we can share them not just amongst the team, but amongst teams across the world. So we feel like these things are going to are going to start to develop some sort of strong meaning. And we're going to have to model these things in a richer way, but right now, this is the place they're at. You define some build types, and then you might define a separate plugin that says, when I have a debug on a GCC, build it with the -G flag. Yeah?
So on Android, for example, if you're trying to debug or release build type, you can do like an open, closure configuration block. Do you set some specific things? It sounds like the intent is to move away from that and then do that in the binaries area by using sort of the combinatorics of different build types, flavors, and things like that.
Yeah, I wouldn't say that's the implementation now. I wouldn't say that the intent is for it to look like this in the future. This is just how it looks now. Like the concept is, like the fact that we're defining build types is important. My feeling is this stuff is probably going to end up in the toolchain definitions. So it's actually, and be able to be extended by plugins. So you sort of have this base, what GCC thinks of a debug variant, and then we have my organization builds debug variants in this way, sort of thing. So, yeah, I wouldn't read into changes to the Android stuff, because it may even be ahead of what we've done in the native space in some of those cases. So the final variant dimension that I want to talk about today is platform. So we've talked about flavors, which is kind of up to you guys to decide what it means. We'll talk about build type, which is there's no canned behavior, but we feel like it's got a pretty strong semantic. And then platform, which is actually built into the current toolchain implementation. So we started off, when we started modeling this, we thought, okay, well, so we've got operating system and we've got architecture. So let's model those as two different dimensions, right? But then you think about architecture and you go, well, actually, that's not one thing. It's like there's a chipset and there's an application binary interface and there's, how big are the different types I'm running and what's the pointer size? And it's like, it just becomes too complicated to model this way, right? It's like if we try to model every possible dimension, then we'll know it'll be like it becomes too complicated to match, becomes too complicated to share with other people and things like that. So we sort of collapsed operating system and architecture. And I guess operating system similar. You say, okay, I'm Windows or Linux, but actually I'm Windows 7 or Windows 8. But actually I'm Windows 7 with Service Pack 3, and then actually I've got these extra libraries that have been installed in another way, and that's actually all part of this, becomes part of this thing we decided, let's think of these as one thing, which is kind of the platform or the runtime that my software is running on. The interesting thing about when we sort of step back and go, okay, let's just simplify it, think of it as a platform, it becomes a more universal concept that applies to a lot of other domains. So what JDK do I run on? That's a platform. What servlet container do I run in? That's your platform. That's your runtime environment. And I'm a binary that can run in. It needs the Servlet 3 API. That becomes part of your runtime requirements, let's say. So it's interesting. Once at first we tried to model it in a lot of detail, and then we stepped back and went, let's kind of keep it simple for now. We'll have named platforms. Maybe they'll become well-known names, and we'll start to publish those in that way we can share things. As long as people agree on what the platforms mean, we can start to share those things. But within an organization, it works well, because usually you define them in one spot, and then you just keep them. So modeling platforms in the native space is pretty straightforward. We basically define that they only have a platform is sort of in concept, it's a flexible set of attributes, right? Right now, what we have is the attributes of operating system and architecture. So we're defining, but this is the important. The actual platform there is the important bit. The toolchain then takes that and goes, okay, I know how to build. Like Visual C++ knows how to build a binary for Windows i386. So it goes, okay, cool. Yeah, I know how to build that, and it'll build it. GCC knows how to build. Or GCC on Linux knows how to build a build for Linux 64 platform. And these are built into the current toolchain implementation. So in general, you don't have to define any more than this. You've noticed I don't have a binaries.all block here saying when you're building that, do this, because that logic is primarily built into the toolchain. There are ways of extending the toolchain adapting the toolchain for your requirements, but in general, that stuff is out of the box.
So specific example of Scala dependency or JDK or Java runtime, where would you model those, or how would you do that?
So it's early days, but so modeling the Java platforms, these sort of, it's conceptual at the moment as opposed to solid. But the question is where would you model the Scala dependency or the Java JDK dependency? The idea is that we're going to move towards a model similar to what we have in the native space. So you'll define platforms. I've defined here the Servlet 3 platform. That's just my name, but it's extending a built-in Java platform, Java 6. So we're saying, okay, these names I've just made up, right? So this actually partly comes from a design spec that we have. So this is actually what we think it might look like. Probably a squiggly bracket there instead of a round one. That would be, that's not going to work real well, but anyway. So we're saying here the Servlet 3, it extends Java 6 and it provides the servlet, a particular version of the Servlet API. So this is just an idea. This is just how we think it might work. But the idea, so thinking about, okay, I can say I want to build for that platform and I want to build for another one. A simple example would be platforms.java6, platforms.java8, and you're building two, and then the tool chains know, okay, I can build for Java 6 and I use target compatibility 6, and then it's done. And then you would have two binaries automatically generated there. Yep.
Right now there's a fixed set of architecture and greater extent.
Yeah, it's just a limitation at the moment. Yeah, the way we've modeled these the architectures and operating systems is, yeah, it was basically, it got, I described how we tried to model everything and it got really complicated. That's when we pared it right back and made it really simple, and we probably went a little bit too far there. So now it's sort of, if you want to define your own architecture, you effectively, if you want to compile for your own architecture, you would define a binary, a platform that doesn't necessarily have any attributes, and then you would say, because the architecture could be implicit within your custom platform. So, which is not a very nice model, but it is the only way you can do it right now. Sorry, there was a question just here.
Yeah, I was going to ask if you have any concept of like a cross-compile build versus I usually say native, but so in other words, can the build system run the executable? And that's not an easy question to answer because like a 64-bit wants 32.
Yeah. So that we do have support for cross-compiler toolchains. So I can talk about it now. So basically, there's some built-in support in the toolchains, which says, okay, I know what the executable is called, and I know what arguments to call to build for this particular architecture and this particular operating system. But then there's actually an API that you can say, I support another platform. So this is actually a very similar question. So we no longer look at the architecture and the operating system. We just say, when you run against this platform, use these executable names and use these arguments with it. So it can actually modify the arguments after they've been generated. So yeah, that's how we sort of support cross-compilation at the moment. So if you have GCC compiled to build for Solaris, and because Solaris we don't have built-in support for Solaris at the moment, but if you have GCC compiled to build for Solaris and it's GCC-Solaris or something, you can configure the executable names and any arguments you need to provide specifically to get Solaris out. Sorry, there's one question at the back. Yep.
So I totally see the platforms in terms of the compilation. Where I started to lose a little bit, this probably because it's still in progress, is when I saw your runtime there with the library and the servlet, that seems to be running into what's specified today, kind of with configurations. Or do I have the wrong mental model?
No, it's right. So this is, and I will talk about this a little bit more in the sort of the domain-specific dependency management, but like right now, the way we declare dependencies on the Servlet API is not a very good way, right? Because what you have to do is you have to use, say, a provided configuration, because actually isn't something you want to include, it's something you just require. So the platforms may be able to provide implementations of some of your dependencies. So you just say, so I might say I need a servlet runtime, and then we can provide that in lots of different ways. We don't have to, so at development time we can provide it in a little Jetty container, and at production, or we can say this, we can deploy to a servlet container that has the same capabilities.
So you take it out of the configuration.
That's right, yes. So, yeah.
Is it possible to remove the built-in support in the toolchain?
So only to, yeah, I think you can, let's have a look at that offline. I won't promise anything. Yeah, if not, we should make it possible. There's a new configure. The the cross-compilation DSL is completely new in 2.0. Like it's the old way is out, and then there's a new way. So, and I can't off the top of my head tell you that. So, yeah. That it? Okay, cool. How am I going? Yeah, good. Okay. So tool chains. I couldn't find a photo of a tool chain, so I got a photo of a chain tool. Is that pretty close? So anyway, Google image search. Yeah. So yeah, a tool chain to us is a set of tools that works together to produce a binary. So it's a really common concept in the native space. So GCC is a tool chain. It has compilers for different languages. It has a linker. And we have Clang, we have Visual C++, which also provide compilers for those language and a linker. So in the Java space, we use a JDK as a tool chain. We basically say, here's my Java compiler I need. Here's my Javadoc generator. There's probably a few other tools we use occasionally for Java. So basically, a tool chain is just a set of tools to work together, and a tool chain knows how to produce a set of produce binaries for a particular set of platforms, and in the future, a set of particular platforms and build types. So that would be kind of our goal, where the logic of what a tool chain is goes. So we now support GCC on Windows, Linux, and Mac. We support Visual C++ on Windows, and a few versions, I think 2008, 2010, and 2013. And we support Clang on Linux, Windows, and Mac as well. So basically, the tool chains, and if you're running without configuring any tool chains, we just try to find the best one for the job. We look in the paths and we go, okay, whichever one we can find, that's the one we'll use, which is really nice when you're just getting up and running. It's more likely in a real environment you'll configure the tool chains you want to use. You'll say, I want to use this particular set of tool chains. And there's definitely some stuff that we want to make better, as people use this more and more, they're going, maybe it works in a restricted environment, but if you want to have a build file that works for every person out there in the world, it becomes pretty tricky to say which tool chains are able to be used and how they need to be used and which ones we prefer. So there's a bit more work there. But what's quite exciting is just yesterday, I think, there was a commit made in the main line of Java, which actually added the Java tool chain. So there's now actually a Java tool chain in Java. It's a sort of a placeholder almost but what it means is, because we had some questions, someone asking on the forum, I want to use the Google error-prone compiler to compile my Java. What do I have to do? Can I set a compiler option and give the path to the compiler? It's like, no, that's not really how we want to model it. Suddenly we're like, we want to model this as a tool chain. So the error-prone compiler can be a Java tool chain. The JDK 1.5 versus JDK 1.8 compilers, they're separate things. They're separate tool chains. It'd be nice to be able to say which one you want to use or to use both or whatever. Similar something like the Zinc compiler for Scala versus Ant-based compilation of Scala. They're different tool chains that do the same thing. So it's kind of exciting to think, wow, we've got this concept now. Now we can actually pull all those hidden options that we've put down in the compiler settings and actually model this at a higher level. And I think that's going to be really powerful coming up. So yeah, Java toolchain will be in 2.1 to some degree, I guess. So this is how we define toolchains in the native space. So I mentioned really early how if you don't define any toolchains, we give you a set of defaults. If you do define them, sometimes you just want to say, I want to use GCC. So this is a way of adding a toolchain named GCC of type GCC. Sometimes you need to give us a bit more configuration. You probably won't need to do this, but if you did need to tell us where your Visual C++ was installed, you would do something along these lines. we do look in the Windows registry to try to find all the installed versions of Visual Studio. So generally, you shouldn't need to do this. Yeah, so that's tool chains. Yep.
So what if you wanted to define the version of GCC?
So so right now you can define the path to GCC, which is kind of a poor man's version of that. So you can't define. What we think we should be able to do is say, I want to use GCC 4.3 and I want to use GCC 3.6. I want to compile with those two versions. Right now, the way you do that is you say, I define a toolchain called GCC 4.3 of type GC3, and you give it the path. The problem is it's then build machine specific and things like that. So ideally, what we would do is look through the path for all the GCCs available, run -v on them, find out what version they are, and then actually find the versions that way. So yeah, that's in the plan, but not in the implementation now.
So is toolchain a variant as well?
No, toolchain's not a variant. It's funny, it actually started off as a variant. So we sort of thought, okay, yeah, toolchain's one of these variant dimensions, but actually, it really isn't, because it's actually a how, not a what. Like, there might be an ABI that's only supported by this. So it might be that all binaries built by this toolchain are only compatible with other binaries built by that toolchain. But that's something about the binary, not something about the toolchain. So, because the problem is, as soon as you say that toolchain is a variant, then you've got to start thinking, that means that GCC ran with those particular flags can actually build a Clang compatible variant or something. We pushed that way for a while, and then it sort of didn't feel right. And it seems like using toolchain as a how rather than a what seems like a better model. So it'd be like saying the JDK you built with is part of your is a variant dimension, as opposed to the JDK you targeted is the variant dimension. Does that make sense?
Well, so what if you wanted to, say, compile against JDK 7 and 8 from the same set of sources?
So why do you want to do that? Sorry, I need to repeat the question. So if you wanted to compile with JDK 7 and JDK 8, we'd want to know why you want to compile with those two.
Let's assume you have 50 million lines of code in a large enterprise and you want to see what it would take to go from 7 to 8 in an automated fashion. So you want to distribute JDK everywhere and then try it out, without having to go to 5 different global offices and tap people on the back and say, hey, could you change your Java home and try this with JDK and let us know how it works. Do you want to do it?
Yeah, so what would we do? We define, we can always, this is a configurable set, so there's no reason you can't change the JDK here. So just remove JDK 8 from the set of tool chains that you're trying to build with. Because it's kind of, it's kind of a, does that make sense? So you're, like if...
What is the semantic meaning of this? If you had both of these in your, what would it, and you type whatever Gradle build,
it will find the first one that can support the platform you're trying to build.
And so you have to run with one, do some programmatic change of the tool chain, and then run it again. You can't do it in a single execution.
Yeah, unless there's, there probably is something different about there's probably something. Yeah, I'm not sure. Yeah, that is the way it works now. There's various ways to do it. I'm trying to think if there's a really nice way to do it that doesn't involve some programmatic change, and I don't know that there is.
Can you create 2 platforms?
So Adam's going to answer this question.
That would be one way to do it, but I think.
Yeah. So I guess it's not a problem we've solved right now with the way, and I don't think that modeling toolchain as a separate variant dimension is really necessarily the way to go, but making it easy to switch between them, or make it easy to, because it comes up occasionally that we need to be able to. I want to use that other toolchain. Why is this one being used? And we often say, well, so why do you want that? And often the reason is, because I have to have it compatible with this, and then that's a what. But you're saying actually, this is not about what you're trying to build. This is an experimental. Let's try something out. So.
Well, one is experimental. The other thing is, how do you do it?
Yeah. So yeah, we should probably pull it back in a little bit. Maybe we should take this decision, because it's definitely a discussion we want to have, is how we can make this stuff richer and what problems are being hit by it. So like we don't think that, like we think we need to be able to model these things better, but we don't know that modeling it just as the same as all the other dimensions is the right way to go. So whoop, we might be wrong. So we'll see. We should try. We should definitely talk about this. But I probably need like 10 minutes left, so I need to move on a little bit. Because is that right, Tim? Yeah. So dependency management. Gee, this projector's really blown out. Anyway. Domain-aware dependency management. So basically dependency management, in Gradle 1.0 we use configurations to define our dependencies, right? And so it begs a question, what the hell is a configuration? Like what, it's sort of this concept that we've inherited from some earlier tooling that sort of comes up with the idea. And it kind of works, but it's an example of modeling. A lot of the time it's an example of modeling the how rather than the what. So we're sort of saying, we define these, and one of the problems with configurations is a lot of the time we don't know what they mean. We don't have a really good, strong semantic around them. They're kind of all the same. Like some of the plugins define named conventions. So I look for a test compile configuration, so I know what's there. But it doesn't really model what you're trying to build that well. So that's one downside, is that the dependency management doesn't really map to our nice new rich domain model. And the other thing is dependency management in Gradle 1.0 is very Java-centric. So I'd mentioned that it's sort of this concept of one jar per project one jar per module is really quite deeply ingrained. So these are a couple of things we need to address in native space, but it already falls down with Scala, for example, with JDK versions. These, we end up using classifiers and things like this, sort of pretty much hacks to get the right artifact for a module. So we wanted to readdress this sort of at a higher level. So we started thinking about and I've said the word a few times. We talked about dimensions, so the variant dimensions. So if you think of what dependency resolution means right now, we say, okay, I've got two different things. One says I need version 1.plus of this, and one says I need version 1.5. What we're doing there is we're going, okay, take the set of candidates available, take 1.plus, all the ones that fit that, take 1.5, and find the intersection of those things, and we now have resolved our dependencies, right? So that's what we're doing right now. What we started thinking about is dependency, like the binary variants, it's sort of this multi-dimensional space of candidates. So let's say we have flavor out here, build type up here, platform down here. We suddenly have, for each version, we have a set of candidates that might meet a particular requirement. So it's not always just one. Sometimes it might be multiple. Like let's say I'm building a debug binary on Linux, GCC. Then it's probably okay for me to, if this library only has a release variant, then that's probably okay. I can use that. So the set is not always. There might be two that are possible. We have to choose the best one. It's really interesting when you start to think, actually, version is just another dimension in this multi-dimensional space of variants. So that's pretty cool to be able to define a problem in terms of multi-dimensional spaces, right? Because what self-respecting geek wouldn't want to do that sort of thing? So, so if you think about how we see dependency management going, is basically going, okay, I've got a requirement for this particular library. That requirement includes a platform it needs to run on, a build type it needs to be built with, and a version it needs to be built. We've tested against, I guess. So here's a set of candidates to work, and then I've got another requirement over here. So we have another set of candidates. So we get the intersection of those, and we can then we can do basically go, okay, here's our set of allowed candidates. Let's choose the best one of those. So that's kind of sort of where we're looking at moving dependency management in the future. So a few things. This is definitely going to need richer dependency metadata. So we can't do this with a pom.xml as being the only metadata. Well, not without some pretty severe extensions to the pom. So the plan is we don't have a really concrete plan, but it's likely that we're going to end up with a new metadata format for defining a much richer set of metadata about what your published variant is. And finally, I want to talk about the native space again. So the way we define dependencies in the native space and how it's more domain aware than what we do in the Java. So effectively in the Java space, this would be a configuration compile for a main so you'd have to give it some compile main and add these libraries. But we're actually just adding dependencies to our main executable. Like we're just saying the main executable depends on a library named hello and depends on a library from project A named B. And I mentioned before we also had the way of defining dependencies at the source level rather than at the component level. So basically by modeling dependencies, by having the dependency management model matched to our actual software component model, it gives us a much richer, more expressive way of stating these things. One interesting thing to think about in the native space is that there's not just even once you've resolved to a single candidate binary for a particular artifact, for a particular library, it's still not just a single file that we're getting back. Because when we're compiling against that library, we need the headers. And when we link against that library, we need the .so or the .lib for a DLL. And then when we at runtime, we may need a different artifact again, depending on the platform we're running on. So the dependency management not only has to handle this sort of handle resolving to a particular variant, but it also needs to handle at different stages in our build, we use that variant in different ways, and we need different artifacts out of that variant. So that's what we have now. For a shared library, we have headers, a link time file, and a runtime file, and that's sort of encapsulated in the dependency management model for the native space. So just quickly, because I've got 5 minutes left. So just to summarize what we talked about today, we're talking about native code support, how it was added, and there's a bunch of new things that were added, as well as just the native language features, which were kind of the driving force behind it. We've added a bunch of new sort of more strategic underlying features, which we think is going to make a big difference to Gradle in the future. A better component model that's going to describe what you're trying to build, rule-based configuration that's going to give you that zero configuration time, as well as a much more flexible way of configuring your plugin interactions, binary variants, which lets you build multiple outputs from the same set of sources, and some domain-aware dependency management. So dependency management is no longer this sort of abstract thing where we go, here's some configurations, give me some files. It's now, I depend on a library and I want to compile against it. I depend on a library, I want to link against it. It becomes a much more domain-aware model. Lots of stuff I haven't talked about today. The need for speed in the native space, which is some of it's going to come from incremental configuration, but also incremental compilation. Haven't talked at all about Visual Studio integration or unit testing integration. So if you want to learn more about the nitty-gritty, feel free to come along to the workshop tomorrow afternoon. And yeah, so that's it. I've got time for a few questions if we want to throw some things out. Yep.
I mean, project A.
Yeah. So there's two different things there. One is sort of this concept of partially building on different machines and then publishing in a sort of a incremental fashion. So building on Windows, building on Solaris, and then publishing all to one place, and then somehow working out, okay, now it's published and we can lock it down. So that's probably going to be our first step towards solving that problem. Long term, what we want to do is, when Hans talked about distribution of Gradle, like making Gradle fully distributable, then we could start thinking about, actually what we do is we find a machine that can find one machine for each of the things we want to build, get them all built, re-aggregate them, and then publish them. But that's probably a step further. I think the first step is going to be a sort of an incremental publish, where we can sort of say, publish parts of it one at a time, and then, okay, now lock down the metadata and say it's done, sort of thing. That's probably more likely what will happen. So I've probably got time for one more question. We haven't done anything on that yet. So we actually build some tools that way, but there's nothing in the Gradle distribution itself that handles that out of the box. So it's Native Platform got examples of that? Yeah, so we use a tool called Native Platform, which is what we use for a lot of our native, talking to different platforms, like getting below the JVM and talking to different things, and we build that with Gradle. So it's actually, if you Google or if you look in GitHub for a thing called native-platform, there'll be an example build script of using our C++ support to build JNO libraries. Yeah, cool. So that's all we got time for. I'm going to be around. I haven't got any more talks. Yeah. But so feel free to come along and hassle me at any time. I'm mostly going to be sitting over in the Gradleware booth. So yeah, thanks for coming along, guys.